time and timekeeping. This chapter covers understanding how a computer keeps time, how operating systems represent timestamps, synchronizing atomic clocks with the Network Time Protocol, or NTP. In this chapter, you'll produce an NTP, or Network Time Protocol client that requests the current time from the world's network of public time servers. It's a fully functioning client that can be included in your own computer's boot process to keep it in sync with the world. Understanding how time works within computers supports your efforts to build resilient applications. The system clock jumps both backwards and forwards in time. Knowing why this happens allows you to anticipate and prepare for that eventuality. Your computer also contains multiple physical and virtual clocks. It takes some knowledge to understand the limitations of each and when these are appropriate. Understanding the limitations of each should foster a healthy skepticism about micro-benchmarks and other time-sensitive code. Some of the hardest software engineering involves distributed systems that need to agree on what time it is. If you have the resources of Google, then you're able to maintain a network atomic clock that provides a worldwide time synchronization of 7 milliseconds. The closest open source alternative is CockroachDB at cockroachlabs.com. It relies on the NTP, which can have a worldwide latency of approximately dozens of milliseconds. But that doesn't make it useless. When deployed within a local network, NTP allows computers to agree on the time within a few milliseconds or less. On the Rust side of the equation, this chapter invests a lot of time interacting with the OS internals. You'll become more competent with unsafe blocks and with using raw pointers. Readers will become familiar with Chrono, the de facto standard crate for high-level time and clock operations. Section 9.1, Background. It's easy to think that a day has 86,400 seconds, or 60 seconds times 60 minutes times 24 hours, which equals 86,400 seconds. But the Earth's rotation isn't quite that perfect. The length of each day fluctuates due to tidal friction with the moon and other effects such as torque at the boundaries of the Earth's core and its mantle. Software does not tolerate these imperfections. Most systems assume that most seconds have an equal duration. The mismatch presents several problems. In 2012, a large number of services, including high-profile sites such as Reddit and Mozilla's Hadoop infrastructure, stopped functioning after a leap second was added to their clocks. And at times, clocks can go back in time. This chapter does not, however, cover time travel. Few software systems are prepared for the same timestamp to appear twice. That makes it difficult to debug the logs. There are two options for resolving this impasse. Keep the length of each second fixed. This is good for computers, but irritating for humans. Over time, midday drifts towards sunset or sunrise. Adjust the length of each year to keep the sun's position relative to noon in the same place from year to year. This is good for humans, but sometimes highly irritating for computers. In practice, we can choose both options as we do in this chapter. The world's atomic clocks use their own time zone with fixed length seconds, called TAI. Everything else uses time zones that are periodically adjusted. These are called UTC. TAI is used by the world's atomic clocks and maintains a fixed length year. UTC adds leap seconds to TAI about once every 18 months. In 1972, TAI and UTC were 10 seconds apart. By 2016, they had drifted to 36 seconds apart. In addition to the issues with the Earth's fickle rotational speed, physics of your own computer make it challenging to keep accurate time. There are also, at least, two clocks running on your system. One is a battery-powered device called the real-time clock. The other one is known as system time. System time increments itself based on hardware interrupts provided by the computer's motherboard. Somewhere in your system, a quartz crystal is oscillating rapidly. Dealing with hardware platforms without a real-time clock. The Raspberry Pi device does not include a battery-supported real-time clock. When the computer turns on, the system clock is set to epoch time. That is, it is set to the number of elapsed seconds since January 1st, 1970. During boot, it uses the NTP to identify the current time. What about situations where there is no network connection? This is the situation faced by the Cacophony Project at cacophony.org.nz, which develops devices to support New Zealand's native bird species by applying computer vision to accurately identify pest species. The main sensor of the device is a thermal imaging camera. Footage needs to be annotated with accurate timestamps. To enable this, the Cacophony Project team decided to add an additional real-time clock, Raspberry Pi Hat, to their custom board. The following figure shows the internals of the prototype for the Cacophony Project's automated pest detection system. Section 9.2. Sources of time. Computers can't look at the clock on the wall to determine what time it is. They need to figure it out by themselves. To explain how this happens, let's consider how digital clocks operate generally. Then, how computer systems operate given some difficult constraints, such as operating without power. Digital clocks consist of two main parts. The first part is some component that ticks at regular intervals. The second part is a pair of counters. One counter increments as ticks occur. The other increments as seconds occur. Determining now within digital clocks means comparing the number of seconds against some predetermined starting point. The starting point is known as the epoch. Embedded hardware aside, when your computer is turned off, a small battery-powered clock continues to run. Its electric charge causes a quartz crystal to oscillate rapidly. The clock measures those oscillations and updates its internal counters. In a running computer, the CPU clock frequency becomes the source of regular ticks. A CPU core operates at a fixed frequency. Inside the hardware, a counter can be accessed via CPU instructions and/or by accessing predefined CPU registers. Footnote 1. Dynamic adjustments to a CPU's clock speed do occur in many processors to conserve power, but these happen infrequently enough from the point of view of the clock as to be insignificant. Footnote 2. For example, Intel-based processors support the RDTSC instruction, which stands for Real Timestamp Counter. Relying on a CPU's clock can actually cause problems in niche scientific and other high-accuracy domains, such as profiling an application's behavior. When computers use multiple CPUs, which is especially common in high-performance computing, each CPU has a slightly different clock rate. Moreover, CPUs perform out-of-order execution. This means it's impossible for someone creating a benchmarking or profiling software suite to know how long a function takes between two timestamps. The CPU instructions requesting the current timestamp may have shifted. Section 9.3. Definitions. Unfortunately, this chapter needs to introduce some jargon. Absolute time describes the time that you would tell someone if they were to ask for the time, also referred to as wall clock time and calendar time. Real-time clock, a physical clock that's embedded in the computer's motherboard, which keeps time when the power is off. It's also known as the CMOS clock. System clock, the operating system's view of the time. Upon boot, the OS takes over timekeeping duties from the real-time clock. All applications derive their idea of time from the system time. The system clock experiences jumps as it can be manually set to a different position. This jumpiness can confuse some applications. Monotonically increasing, a clock that never provides the same time twice. This is a useful property for a computer application because, among other advantages, log messages will never have a repeated timestamp. Unfortunately, preventing time adjustments means being permanently bound to the local clock skew. Note that the system clock is not monotonically increasing. Steady clock. This clock provides two guarantees. Its seconds are equal length, and it is monotonically increasing. Values from steady clocks are unlikely to align with this system clock's time or absolute time. These typically start at 0 when computers boot up, then count upwards as an internal counter progresses. Although potentially useless for knowing the absolute time, these are handy for calculating the duration between 2 points in time. High accuracy. A clock is highly accurate if the length of its seconds are regular. The difference between two clocks is known as skew. Highly accurate clocks have little skew against the atomic clocks that are humanity's best engineering effort at keeping accurate time. High resolution provides accuracy down to 10 nanoseconds or below. High-resolution clocks are typically implemented within CPU chips because there are few devices that can maintain time at such high frequency. CPUs are able to do this. Their units of work are measured in cycles, and cycles have the same duration. A 1 GHz CPU core takes 1 nanosecond to compute one cycle. Fast clock. A clock that takes little time to read the time. Fast clocks sacrifice accuracy and precision for speed, however. Section 9.4. Encoding time. There are many ways to represent time within a computer. The typical approach is to use a pair of 32-bit integers. The first counts the number of seconds that have elapsed. The second represents a fraction of a second. The precision of the fractional part depends on the device in question. The starting point is arbitrary. The most common epoch in Unix-based systems is the 1st of January 1970 UTC. Alternatives include the 1st of January of 1900, which happens to be used by NTP, the 1st of January 2000 for more recent applications, and the 1st of January 1601, which is the beginning of the Gregorian calendar. Using fixed-width integers presents two key advantages and two main challenges. Advantages include simplicity. It's easy to understand the format. Efficiency. Integer arithmetic is the CPU's favorite activity. Disadvantages include fixed range. All fixed integer types are finite, implying that time eventually wraps around to 0 again. Imprecise. Integers are discrete, while time is continuous. Different systems make different trade-offs relating to sub-second accuracy, leading to rounding errors. It's also important to note that the general approach is inconsistently implemented. Here are some things seen in the wild to represent the seconds component. Unix timestamps, a 32-bit integer, represents milliseconds since epoch, or the 1st of January 1970. MS Windows file time structures, since Windows 2000, a 64-bit unsigned integer, represents 100 nanosecond increments since the 1st of January 1601 UTC. Rust Community's Chronos Crate, a 32-bit signed integer, implements naive time alongside an enum to represent time zones where appropriate. Footnote 3. Chronos has relatively few quirks, but one of which is sneaking leap seconds into the nanoseconds field. Time_t, meaning time type, but also called simple time or calendar time, within the C standard library, libc, varies. Dinkemware's libc provides an unsigned long int, e.g. a 32-bit unsigned integer. News libc includes a long int, e.g. a 32-bit signed integer. AVR's libc uses a 32-bit unsigned integer, and its epoch begins at midnight, the 1st of January 2000, UTC. Fractional parts tend to use the same type as their whole second counterparts, but this isn't guaranteed. Now, let's take a peek at time zones. Section 9.4.1. Representing time zones. Time zones are political divisions, rather than technical ones. A soft consensus appears to have been formed around storing another integer that represents the number of seconds offset from UTC. Section 9.5. Clock, version 0.1.0. Teaching an application how to tell time. To begin coding our NTP client, let's start by learning how to read time. Figure 9.1 provides a quick overview of how an application does that. Listing 9.2, which reads the system time in the local time zone, might almost feel too small to be a full-fledged example. But running the code results in the current timestamp formatted according to the ISO 8601 standard. The following listing provides its configuration. You'll find the source for this listing in this file. The following listing reads and prints the system time. You'll find the source code for the listing in this file. In listing 9.2, there's a lot of complexity hidden by these 8 lines of code. Much of it will be peeled away during the course of the chapter. For now, it's enough to know that Chronos local provides the magic. It returns a typed value containing a time zone. Note: interacting with timestamps that do not include time zones or perform other forms of illegal time arithmetic results in the program refusing to compile. Section 9.6. Clock version 0.1.1. Formatting timestamps to comply with ISO 8601 and email standards. The application that we'll create is called Clock, which reports the current time. You'll find the full application in listing 9.7. Throughout the chapter, the application will be incrementally enhanced to support setting the time manually and via NTP. For the moment, however, the following code shows us the result of compiling and running the code from listing 9.8 and sending it the --use standard timestamp flag. Section 9.6.1. Refactoring the Clock version 0.1.0 code to support a wider architecture. It makes sense to spend a short period of time creating a scaffold for the larger application that Clock will become. Within the application, we'll first make a small cosmetic change. Rather than using functions to read the time and adjust it, we'll use static methods of a clock struct. The following listing, an excerpt from listing 9.7, shows the change from listing 9.2. What on earth is the return type of set? The exclamation mark indicates to the compiler that the function never returns. A return value is impossible. It's referred to as the never type. If the unimplemented exclamation point macro, or its shorter cousin to-do exclamation point, is reached at runtime, then the program panics. Clock is purely acting as a namespace at this stage. Adding a struct now provides some extensibility later on. As the application grows, it might become useful for Clock to contain some state between calls or implement some trait to support new functionality. Note: a struct with no fields is known as a zero-sized type, or ZST. It does not occupy any memory in the resulting application and is purely a compile time construct. Section 9.6.2. Formatting the time. This section looks at formatting the time as a Unix timestamp, or a formatted string, according to ISO 8601, RFC 2822, and RFC 3339 conventions. The following listing, an excerpt from the listing 9.7, demonstrates how to produce timestamps using the functionality provided by Chrono. The timestamps are then sent to standard out. Our Clock application, thanks to Chrono, supports 3 time formats: timestamp, RFC 2822, and RFC 3339. Timestamp formats the number of seconds since the epoch, also known as a Unix timestamp. RFC 2822 corresponds to RFC 2822. See this link, which is how time is formatted within email message headers. RFC 3339 corresponds to RFC 3339, visible at this link. RFC 3339 formats time in a way that is more commonly associated with the ISO 8601 standard. However, ISO 8601 is a slightly stricter standard. Every RFC 3339 compliant timestamp is also an ISO 8601 compliant timestamp, but the inverse is not true. Section 9.6.3. Providing a full command line interface. Command line arguments are part of the environment provided to an application from its OS when it's established. These are raw strings. Rust provides some support for accessing the raw vec of string via std, env, args, but it can be tedious to develop lots of parsing logic for moderately sized applications. Our code wants to be able to validate certain input, such that the desired output format is one that the clock app actually supports. But validating input tends to be irritatingly complex. To avoid this frustration, Clock makes use of the clap crate. There are two main types that are useful for getting started: clap app and clap arg. Each clap arg represents a command line argument and the options that it can represent. Clap app collects these into a single application. To support the public API in Table 9.1, the code in Listing 9.5 uses three arg structs that are wrapped together within a single app. Listing 9.5 is an excerpt from Listing 9.7. It demonstrates how to implement the API presented in Table 9.1 using clap. Clap automatically generates some usage documentation for our clock application on your behalf. Using the --help option triggers its output. Section 9.6.4. Clock version 0.1.1 Full Project. The following terminal session demonstrates the process of downloading and compiling the Clock version 0.1.1 project from the public Git repository. It also includes a fragment for accessing the --help option that is mentioned in the previous section. Creating the project step by step takes slightly more work. As Clock version 0.1.1 is a project managed by Cargo, it follows the standard structure. To create it manually, follow these steps. 1. From the command line, execute these commands. 2. Compare the contents of your project's cargo.toml file with Listing 9.6. With the exception of the authors field, these should match. 3. Replace the contents of src/main.rs with Listing 9.7. The next listing is the project's cargo.toml file. You'll find it at ch9/ch9-clock1/cargo.toml. Following that is the project's src/main.rs file, Listing 9.7. Its source is in ch9/ch9-clock/src/main.rs. Section 9.7. Clock version 0.1.2. Setting the time. Setting the time is complicated because each OS has its own mechanism for doing so. This requires that we use OS-specific conditional compilation to create a cross-portable tool. Section 9.7.1. Common behavior. Listing 9.11 provides two implementations of setting the time. These both follow a common pattern. 1. Parsing a command line argument to create a date time of fixed offset value. The fixed offset time zone is provided by Chrono as a proxy for whichever time zone is provided by the user. Chrono doesn't know at compilation time which time zone will be selected. 2. Converting date time of fixed offset to a date time of local to enable time zone comparisons. 3. Instantiating an OS-specific struct that is used as an argument for the necessary system call. System calls are function calls provided by the OS. 4. Setting the system's time within an unsafe block. This block is required because responsibility is delegated to the OS. 5. Printing the updated time. Warning. This code uses functions to teleport the system's clock to a different time. This jumpiness can cause system instability. Some applications expect monotonically increasing time. A smarter but more complex approach is to adjust the length of a second for n seconds until the desired time is reached. Functionality is implemented within the clock struct that was introduced in Section 9.6.1. Section 9.7.2. Setting the time for the operating system that uses libc. POSIX-compliant operating systems can have their time set via a call to set time of day, which is provided by libc. Libc is the C standard library and has lots of historic connections with Unix operating systems. The C language, in fact, was developed to write Unix. Even today, interacting with a Unix derivative involves using the tools provided by the C language. There are two mental hurdles required for Rust programmers to understand the code in Listing 9.11, which we'll address in the following sections. The arcane types provided by libc. The unfamiliarity of providing arguments as pointers. libc type naming conventions. libc uses conventions for naming types that differ from Rust's. libc does not use Pascal case to denote a type, preferring to use lowercase. That is, where Rust would use timeval where T and V are capitalized, libc uses all lowercase timeval. The convention changes slightly when dealing with the type aliases. Within libc, type aliases append an underscore followed by the letter T, or underscore T, to the type's name. The next two snippets show some libc imports and the equivalent Rust code for building those types. On line 64 of Listing 9.8, you will encounter this line. It represents two type aliases and a struct definition. In Rust syntax, these are defined like this. Time underscore T represents the seconds that have elapsed since the epoch. SU seconds underscore T represents the fractional component of the current second. The types and functions relating to timekeeping involve a lot of interaction. The code is intended to be easy to implement, which means providing local implementers, hardware designers, the opportunity to change aspects as their platforms require. The way this is done is to use type aliases everywhere, rather than sticking to a defined integer type. Non-Windows clock code. The libc library provides a handy function, setTimeOfDay, which we'll use in Listing 9.8. The project's cargo.toml file requires 2 extra lines to bring libc bindings into the crate for non-Windows platforms. The following listing, an extract from Listing 9.11, shows how to set the time with C's standard library, libc. In the listing, we use Linux and BSD operating systems or other similar ones. Makes OS-specific imports within the function to avoid polluting the global scope. libc setTimeOfDay is a function that modifies the system clock, and SU seconds underscore T, time underscore T, timeval, and time zone are all types used to interact with it. This code cheekily and probably perilously avoids checking whether the setTimeOfDay function is successful. It's quite possible that it isn't. That will be remedied in the next iteration of the clock application. Section 9.7.3. Setting the time on MS Windows. The code for MS Windows is similar to its libc peers. It is somewhat wordier as the struct that sets the time has more fields than the second and subsecond part. The rough equivalent of the libc library is called kernel32.dll, which is accessible after including the Win API crate. Windows API integer types. Windows provides its own take on what to call integer types. This code only makes use of the word type, but it can be useful to remember the other two common types that have emerged since computers have used 16-bit CPUs. The following table shows how integer types from kernel32.dll correspond to Rust types. Representing time in Windows. Windows provides multiple time types. Within our clock application, however, we're mostly interested in system time. Another type that is provided is file time. The following table describes these types to avoid confusion. Windows clock code. As the system time struct contains many fields, generating one takes a little bit longer. The following listing shows this construct. Section 9.7.4. Clock version 0.1.2. The full code listing. Clock version 0.1.2 follows the same project structure as version 0.1.1, which is repeated here. To create platform-specific behavior, some adjustments are required to cargo.toml. Listings 9.10 and 9.11 provide the full source code for the project. These are available for download from ch9/ch9-clock0/cargo.toml and ch9/ch9-clock0/src/main.rs, respectively. Section 9.8. Improving error handling. Those readers who have dealt with operating systems before will probably be dismayed at some of the code in Section 9.7. Among other things, it doesn't check to see whether calls to set time of day and set system time were actually successful. There are multiple reasons why setting the time might fail. The most obvious one is that the user who is attempting to set the time lacks permission to do so. The robust approach is to have clock set of t return result, as that requires modifying two functions that we have already spent some time explaining in depth. Let's introduce a workaround that instead makes use of the operating system's error reporting. After calls to clock set of t, Rust happily talks to the OS via std io err last _os _error. Rust checks to see if an error code has been generated. Section 9.9. Clock version 0.1.3. Resolving differences between clocks with the Network Time Protocol, or NTP. Coming to a consensus about the correct time is known formally as clock synchronization. There are multiple international standards for synchronizing clocks. This section focuses on the most prominent one, the Network Time Protocol, or NTP. NTP has existed since the mid-1980s, and it has proven to be very stable. Its on-wire format has not changed in the first 4 revisions of the protocol, with backwards compatibility retained the entire time. NTP operates in 2 modes that can loosely be described as always-on and request/response. The always-on mode allows multiple computers to work in a peer-to-peer fashion to converge on an agreed definition of now. It requires a software daemon or service to run constantly on each device, but it can achieve tight synchronization within local networks. The request-response mode is much simpler. Local clients request the time via a single message and then parse the response, keeping track of the elapsed time. The client can then compare the original timestamp with the timestamp sent from the server, alter any delays caused by network latency, and make any necessary adjustments to move the local clock towards the server's time. Which server should your computer connect to? NTP works by establishing a hierarchy. At the center is a small network of atomic clocks. There are also national pools of servers. NTP allows clients to request the time from computers that are closer to atomic clocks, but that only gets us part of the way. Let's say your computer asks 10 computers what they think the time is. Now we have 10 assertions about the time, and the network lag will differ for each source. Section 9.9.1. Sending NTP requests and interpreting responses. Let's consider a client-server situation where your computer wants to correct its own time. For every computer that you check with, let's call these time servers, there are 2 messages. The message from your computer to each time server is the request. The reply is known as the response. These 2 messages generate 4 time points. Note that these occur in serial. T1, the client's timestamp for when the request was sent, referred to as T1 in the code. T2, the time server's timestamp for when the request was received, referred to as T2 in code. T3, the time server's timestamp for when it sends the response, referred to as T3 in code. T4, the client's timestamp for when the response was received, referred to as T4 in code. The names T1 through T4 are designated by the RFC 2030 specification. Figure 9.2 shows the timestamps. To see what this means in code, spend a few moments looking through the following listing. Lines 2 through 12 deal with establishing a connection. Lines 14 through 21 produce T1 through T4. T1 through T4, encapsulated in listing 9.12 as NTP result, are all that's required to judge whether the local time matches the server's time. The protocol contains more related to error handling, but that's avoided here for simplicity. Otherwise, it's a perfectly capable NTP client. Section 9.9.2. Adjusting the local time as a result of the server's response. Given that our client has received at least one, and hopefully a few more, NTP responses, all that's left to do is calculate the right time. But wait, which time is right? All we have are relative timestamps. There is still no universal truth that we've been given access to. Note: for those readers who don't enjoy Greek letters, feel free to skim or even skip the next few paragraphs. The NTP documentation provides two equations to help resolve the situation. Our aim is to calculate two values. Table 9.2 shows the calculations. The time offset is what we're ultimately interested in. It is denoted as theta by the official documentation. When theta is a positive number, our clock is fast. When it is negative, our clock is slow. The delay caused by network congestion, latency, and other noise. This is noted as delta. A large delta implies that the reading is less reliable. Our code uses this value to follow servers that respond quickly. The mathematics can be confusing because there is always an innate desire to know what the time actually is. That's impossible to know. All we have are assertions. NTP is designed to operate multiple times per day, with participants nudging their clocks incrementally over time. Given sufficient adjustments, theta tends to zero while delta remains relatively stable. The standard is quite prescriptive about the formula to carry out the adjustments. For example, the reference implementation of NTP includes some useful filtering to limit the effect of bad actors and other spurious results. But we're going to cheat. We'll just take a mean of the differences weighted by 1 over theta squared. This aggressively penalizes slow servers to minimize the likelihood of any negative outcomes. We'll check the time with known good actors. In particular, we'll use time servers hosted by major OS vendors and other reliable sources to minimize the chances of someone sending us a questionable result. No single result will affect the result too much. We'll provide a cap of 200 milliseconds on any adjustment we make to the local time. The following listing, an extract from listing 9.15, shows this process for multiple time servers. Section 9.9.3, converting between time representations that use different precisions and epochs. Chrono represents the fractional part of a second, down to a nanosecond precision, whereas NTP can represent times that differ by approximately 250 picoseconds. That's roughly 4 times more precise. The different internal representations used imply that some accuracy is likely to be lost during conversions. The from trait is the mechanism for telling Rust that two types can be converted. From provides the from method, which is encountered early on in one's Rust career. In examples such as string, from of hello world surrounded in quotes. The next listing, a combination of 3 extracts from listing 9.15, provides implementations of the std convert from trait. This code enables the .into calls on lines 28 and 34 of listing 9.13. From has a reciprocal peer, into, Implementing from allows Rust to automatically generate an into implementation on its own, except in advanced cases. In those cases, it's likely that developers already possess the knowledge required to implement into manually, and so probably don't need assistance here. Section 9.9.4. Clock version 0.1.3. The full code listing. The complete code listing for our clock application is presented in Listing 9.15. Taken in its full glory, the whole of the clock application can look quite large and imposing. Hopefully, there is no new Rust syntax to digest within the listing. The source for this listing is in this file. Summary. Keeping track of elapsed time is difficult. Digital clocks ultimately rely on fuzzy signals from analog systems. Representing time is difficult. Libraries and standards disagree about how much precision is required and when to start. Establishing truth in a distributed system is difficult. Although we continually deceive ourselves otherwise, there is no single arbiter of what time it is. The best we can hope for is that all of the computers in our network are reasonably close to each other. A struct with no fields is known as a zero-size type or ZST. It does not occupy any memory in the resulting application and is purely a compile-time construct. Creating cross-portable applications is possible with Rust. Adding platform-specific implementations of functions requires the precise use of the CFG annotation, but it can be done. When interacting with external libraries, such as the API provided by the operating system, or OS, a type conversion step is almost always required. Rust's type system does not extend to libraries that it did not create. System calls are used to make function calls to the OS. This invokes a complex interaction between the OS, the CPU, and the application. The Windows API typically uses verbose Pascal case identifiers, whereas operating systems from the POSIX tradition typically use terse lowercase identifiers. Be precise when making assumptions about the meaning of terms such as epoch and time zone. There's often hidden context lurking beneath the surface. Time can go backwards. Never write an application that relies on monotonically increasing time without ensuring that it requests a monotonically increasing clock from the OS. Chapter 10. Processes, Threads, and Containers. This chapter covers concurrent programming in Rust, how to distinguish processes, threads, and containers, channels and message passing, task queues. So far, this book has almost completely avoided two fundamental terms of system programming, threads and processes. Instead, the book has used the single term, program. This chapter expands our vocabulary. Processes, threads, and containers are abstractions created to enable multiple tasks to be carried out at the same time. This enables concurrency. Its pure term, parallelism, means to make use of multiple physical CPU cores at the same time. Counterintuitively, it is possible to have a concurrent system on a single CPU core. Because accessing data from memory and I/O take a long time, threads requesting data can be set to a blocked state. Blocked threads are rescheduled when their data is available. Concurrency, or doing multiple things at the same time, is difficult to introduce into a computer program. Employing concurrency effectively involves both new concepts and new syntax. The aim of this chapter is to give you the confidence to explore more advanced material. You will have a solid understanding of the different tools that are available to you as an applications programmer. This chapter exposes you to the standard library and the well-engineered crates, Crossbeam, and Rayon. It will enable you to use them, though it won't give you sufficient background to be able to implement your own concurrency crates. The chapter follows the following structure. It introduces you to Rust closure syntax in section 10.1. Closures are also known as anonymous functions and lambda functions. The syntax is important because the standard library and many, perhaps all, external crates rely on that syntax to provide support for Rust's concurrency model. It provides a quick lesson on spawning threads in section 10.2. You'll learn what a thread is and how to spawn those. You'll also encounter a discussion of why programmers are warned against spawning tens of thousands of threads. It distinguishes between functions and closures in section 10.3. Conflating these two concepts can be a source of confusion for programmers new to Rust, as these are often indistinguishable in other languages. It follows with a large project in section 10.4. You'll implement a multi-threaded parser and code generator using multiple strategies. As a nice aside, you get to create procedural art along the way. The chapter concludes with an overview of other forms of concurrency. This includes processes and containers. Section 10.1. Anonymous functions. This chapter is fairly dense, so let's get some points on the board quickly with some basic syntax and practical examples. We'll circle back to fill in a lot of the conceptual and theoretical material. Threads and other forms of code that can run concurrently use a form of function definition that we've avoided for the bulk of the book. Take a look at it now. Defining a function looks like this. The loosely equivalent lambda function is... Lambda functions are denoted by the pair of vertical bars, followed by curly brackets. The pair of vertical bars lets you define arguments. Lambda functions in Rust can read variables from within their scope. These are closures. Unlike regular functions, lambda functions cannot be defined in global scope. The following listing gets around this by defining one within its main. It defines two functions, a regular function and a lambda function, and then checks that these produce the same result. When you run listing 10.1, it executes happily and silently. Let's now see how to put this functionality to work. Section 10.2. Spawning threads. Threads are the primary mechanism that operating systems provide for enabling concurrent execution. Modern operating systems ensure that each thread has fair access to the CPU. Understanding how to create threads, often referred to as spawning threads, and understanding their impact are fundamental skills for programmers wanting to make use of multi-core CPUs. Section 10.2.1. Introduction to closures. To spawn a thread in Rust, we pass an anonymous function to std thread spawn. As described in section 10.1, anonymous functions are defined within two vertical bars to provide arguments and then curly brackets for the function's body. Because spawn doesn't take any arguments, you will typically encounter this syntax. When the spawn thread wants to access variables that are defined in the parent scope, called a capture, Rust often complains that captures must be moved into the closure. To indicate that you want to move ownership, anonymous functions take a move keyword. Why is move required? Closures spawned in subthreads can potentially outlive their calling scope. As Rust will always ensure that accessing the data is valid, it requires ownership to move to the closure itself. Here are some guidelines for using captures while you gain an understanding of how these work. To reduce friction at compile time, implement compy. Values originating in outer scopes may need to have a static lifetime. Spawned subthreads can outlive their parents. That implies that ownership should pass to the subthread with move. Section 10.2.2. Spawning a thread. A simple task waits, sleeping the CPU for 300 milliseconds. If you have a 3 GHz CPU, you're getting it to rest for nearly 1 billion cycles. Those electrons will be very relieved. When executed, listing 10.2 prints the total duration, in wall clock time, of both executing threads. Here's the output. If you had encountered multi-threaded programming before, you would have been introduced to join on line 11. Using join is fairly common, but what does it mean? Join is an extension of the thread metaphor. When threads are spawned, these are said to have forked from the parent thread. To join threads means to weave these back together again. In practice, join means wait for the other thread to finish. The join function instructs the OS to defer scheduling the calling thread until the other thread finishes. Section 10.2.3. Effect of spawning new threads. In ideal settings, adding a second thread doubles the work we can do in the same amount of time. Each thread can get its work done independently. Reality is not ideal, unfortunately. This has created a myth that threads are slow to create and bulky to maintain. This section aims to dispel that myth. When used as intended, threads perform very well. Listing 10.3 shows a program that measures the overall time taken for two threads to perform the job that was carried out by a single thread in listing 10.2. If adding threads takes a long time, we would expect the duration of listing 10.3's code to be longer. As you'll notice, there's a negligible impact from creating one or two threads. As with listing 10.2, listing 10.3 prints almost the same output. The difference in these two runs on my computer was 0.24 milliseconds. While by no means a robust benchmark suite, it does indicate that spawning a thread isn't a tremendous performance hit. If you've had any experience to the field before, you may have heard that threads don't scale. What does that mean?